exponent of a complex number. So in this video we are going to discuss or go over complex number, and it's called exponents. So let's see a complex number exponent with respect to rational exponent. Okay, so here you see the quotes. I mean, not the quote, of course. Newton remarked this as if quotes had lived, we might have known something. So we'll see some history here. Okay, so when we multiply here, when multiplying complex number in polar form, you add the argument, right? If you have z1 plus z1 times z2, so you are going to add the argument. So argument of z1 plus argument of z2. Okay, we have two complex number. And when multiplying power of the same base, for example, a to the power of m times a to the power of n, you are going to add the exponent a to the power of m and n. There is some kind of relation here. Some kind of relation. This suggests there might be a link between a familiar expression of complex number and seemingly remote territory of the exponential functions. This was first noticed in 1714, okay, by the young Englishman Roger Cotes, 2 years before his death at the age of 28. When Newton remarked, if Cotes had lived, we might have known something. So there is a relationship between complex exponent and exponential let it be function, of course. Okay, and made widely known through the influential book published by Euler in 1748. Okay, so we can see here the relationship between exponent power, especially with respect to the exponent, and here the complex number exponent. All right, let's see some problem here. If you have a complex number z1, let it be 1. Okay, let it be 2 in polar form. Cosine of power 3 plus I sine, let it be power 3. Okay, but if you want to multiply z like twice square or 3 times 4 times by itself, let it be z to the power of, let's start with z2. Okay, what will happen here? You are going to multiply z by itself, right? As you know, just to revise, z1 times z2, if you have two complex number having different magnitude, so you are going to multiply the modulus, and you are going to add the two arguments, plus I sine theta 1 plus theta 2. But the point is, what if theta argument, the two arguments are equal in magnitude, which is the same as theta? So this is the same as, again, let it be the gap or the distance from the origin to those complex number will be equal. Let it be r1 is the same as r2, which is equals to r. So as you can see here, if we change to the same base, that is r times r, we have the exponent here 1 1, and cosine of, and instead of theta 1 and theta 2, you just substitute just theta. That goes to theta plus theta. Okay, theta plus theta. Of course, you can prove this through integration. Sine theta plus theta. Okay, this is the same as, since the base is the same, you can add the exponent, which is 2. Cosine of, now you have 2 here, twice of theta plus I sine twice of theta. Okay, as you can see here, this 2 exponent is the same as here. Okay, so when you work this, for example, z to the power of 5, this is the same as r to the power of 5. Okay, cosine of 5 theta plus I, okay, sine 5 theta. So to come to generalize, all right, z to the power of n is the same as r to the power of n over, cosine of n theta plus I sine n theta. So our question was z is equals to 2 into cosine of pi over 3 plus I sine pi over 3. And then if we're asked to make squared, this is the same as 2 squared. Cosine of twice of pi over 3 means 2 pi over 3 plus I sine 2 pi over 3. This is the power of the exponent. Okay, let's solve this problem. There comes the power of the exponent and the polar form. So it is too difficult to solve this problem. Just multiplying this one 48 times. So it's very difficult, or it takes time to solve this problem. So thank you for the polar form and the exponent form of complex number, so that we can easily solve this problem. Okay, so the first step is change this both the numerator and denominator to polar form. So let's do the first one. So the first one, let's find argument. Okay, argument, let this one is z1, of course, just to make it this is z2. So argument of z1 is tan inverse of 1 over negative root 3. This is the same as negative tan inverse of 1 over 3. So that is pi over 6 minus, this is the same as pi over minus pi over 6. Okay, let's find the magnitude or modulus of z1 or r, which is the same as negative root 3 the whole squared plus 1 squared. Okay, this goes to 3 plus 1, which is 4. The square root of 4 is 2. Okay, so our polar form of z1 will be r. R is 2 into cosine of minus pi over 6 plus I sine minus pi over 6. Okay, now let's do the second one here. Let me use this. Okay, so z2 is 1 minus I. So let's find argument of z2, which is tan inverse of minus 1 over 1, which is negative of tan inverse of 1. Okay, that goes to 45 degree, negative pi over 4. So the modulus z2 or r is the square root of 1 squared plus minus 1 squared, which is the square root of 2. So the polar form of z2 will be r, which is the square root of 2 into cosine of minus pi over 4 plus I sine pi over 4, negative pi over 4. Okay, this is it. So let's substitute here. Let's plug it here. Okay, let me slide it here. Okay, so that means we have 48 as a power. So the first one is, okay, that is going to be, we have 48. So 2 into cosine of, okay, since cosine is even function, let's write the positive one, positive pi over 6 minus I sine pi over 6. Okay, divided by here the square root of 2 into cosine of, again, let's use the positive one, cosine of pi over 4 minus I sine pi over 4. Okay, the big to the power of 48. Okay, so let's use the property. Yeah, let's use the property. This is the same as 2 to the power of 48 times cosine of pi over 6 times 48. Okay, minus, let me move this one, minus I sine pi over 6 times 48. over, do the same thing here. The square root of 2 is 2 to the power of 1 over 2 times we have 48, okay, over cosine of pi over 4 times 48 minus I sine pi over 4 times 48. Okay, now let's move the slide a bit so that will be clear. So this is the same as, since the base here, okay, let's finish up. 2 to the power of 48 over 2 to the power of half of 48 here is 24, okay, into, there you have 48 divided by 6 is 8, so cosine of 8 pi minus I sine 8 pi, okay, over, there you have cosine of, I think, 12, cosine of 12 pi, yeah, 12 pi minus I sine 12 pi. Okay, so in this case we have to apply exponential rule. Since the base is the same, we're going to subtract the exponent, and also we can apply here two polar form of complex number. When you divide, just subtract the argument. Cosine of 8 pi minus 12 pi, okay, minus sine 8 pi minus 12 pi. But still we have 48 as a power here. No, we already finished that. Okay, so let's finish up. This is the same as 2 to the power. When you subtract, you have 24 into cosine of negative 4 pi, okay, minus I sine minus 4 pi. So again, since 2 to the power 4, this is the same as cosine of 4 pi, okay, so this is the same as, since it is sine is odd function, that negative multiply this as positive, so plus I sine 4 pi. So this is in short the answer, okay, in polar form. Of course you can change this to Cartesian form. So this is the power or the use of exponent when you divide and multiply a very big complex number.